online tutor and went ahead, like I mentioned, to discs and, well, that's all discs. Wait for it. And washers. To discs and washers. But first of all, let's see where the need arose from. In some ways, it's just like cross-sectional areas, and in some ways, it is very, very different. Did you guys figure out, based on the question up above, exactly what part of this we were rotating? Was it the whole thing? Was it this part, that part, this part, that part? First quadrant. Good. I don't think I want black. Hold on. I want something lighter so that it doesn't... Oh, we could do crayon. That works. Okay, so we're trying to do this region, right? And where or how are we supposed to be rotating that region? Around the x-axis. So we're spinning it here. Now, guys, is it a perfect paraboloid from last year? No. Because you see how it came to this weird little point? And then it's going to go out from that point? Now, technically, 1, 2, 3, 4, 5... 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. If it's going to spin, it's going to spin in the exact same location. But also, it's like a top. If you want to think spinning a top. In that it is going to be like a paraboloid, but the paraboloid was a little different, because remember the paraboloid was more like a cup, right? This one comes to a point, but it's super similar as far as the shape. Now, whatever the shape is, remember how I said just a second ago, what if you were to slice this guy? And it's going to get a little bit harder to visualize. Let me do blue. I think it will stick out more. But if we slice it, and if we give it some depth, which if we sliced it, it would be kind of ridged like we saw yesterday with our, oh, here he is. It would be kind of ridged. But remember, the integral is what makes it perfect, so it is going to kind of jut out, but then it's going to get perfect in a little bit. You guys mentioned how this is a circular cross-section, right? So guys, it's easy. No big deal. How do we make volume formulas? Volume equals, okay. It is dx, like someone mentioned. If AJ, I think that was you. Others of you probably figured that out. It is a dx. We mentioned how the area of any circular cross-section is going to be pi r squared, right? So what are my bounds, cool kids? Any ideas? 0 to, how'd you figure out 4? Yeah, you could do it a few different ways. We are doing x bounds from the left and to the right. Left is 0, right is, well, we could if we were allowed to use our calculator, which we are because of the decimals. Couldn't we do the zeros of the function, like where it hits the x-axis? Sweet. So we could actually have found it. Or isn't it also when y equals 0, and this one is basic to solve by hand? Some of you are like, basic. Basic. There's a 3/2 power. That's okay. What do we do with it? We can move it. We can divide by a negative. How do we undo? Come on. Raise it to the second would be part of it. 2/3. Why not just cross it all out, right? So now we have to raise him to the 2/3. Okay, now we have the dilemma of x, because that reduces, that reduces, that reduces. I had some people in here after school doing an AP practice problem, and they were like, how do we do powers again? Okay, help. How do we do powers? We're not deriving or integrating though. Like how do we just get to x? X is what? How do I do 8 to the 2/3? Cubed root. You guys agree? So the cubed root is 64, and you're like, some of you know that's 4. Another way of doing it, though, couldn't you have made 8 2 cubed? Why would that have been nice? The 3's cancel, and you end up with 2 squared, which is 4. So whether you actually go through all the work of 8 squared being 64, the cubed root of 64 is, I don't know, what times what times what is 64? 4 times 4 times 4. Got him. Or whether you say, he can be broken down. Either way, you get 4. So those people that said 0 to 4, were they right? Yeah, they were. Okay, what comes next in our volume formula, cool kids? We have our bounds. We know it's dx. Now what? Area, good. So it's pi. Uh-oh, what haven't we thought about yet? R. Now hold on, I'm going to get out of here. I'm going to go here. Is top minus bottom? Is R 2? What's R? What do you guys see? How is this circle different from these circles? Where were they? This was our, where's my crayon? There's my crayon. This was our region, right? And it was growing up out of it. Period 6 yesterday had the epiphany of Popsicle Man from, I don't know, some sort of movie. Popsicle Man was like melting and then he would grow back up. Anyway, you can think about that with volumes of cross sections. You have this base, this foundation. Maybe you guys don't know Popsicle Man. They were very excited. But it grows up out of like a puddle or of some sort of, it grows up out of this foundation. What was right minus left here? Radius or diameter? Diameter, because the circle, if it was to keep going, this is the diameter. How about this semicircle one? Where was he? Here he is. Here was our region. Growing up out of him. What was top minus bottom? Diameter, because it was growing up out of that, right? What's different once we start revolving? Top minus bottom revolves. So since top minus bottom revolves, is top minus bottom diameter or radius? Yeah, do you see the difference? If it's growing up out of this puddle, your whole circle, the diameter, is founded or bounded by right minus left or top minus bottom. But if that's spinning, well, now all of a sudden you have more region being covered. So that's what's going to be a little bit different in that R is equal to top minus bottom. Well, if R is equal to top minus bottom, who was on the top? Wasn't it this guy? And who's on the bottom? Yeah, it's just the x-axis, which is y equals 0. So I can go ahead and put in my 8 minus x to the 3/2 minus 0. Now, what's something that we need to figure out whenever we tackle one of these problems in homework? What's your big question if you're able to get here as to how to proceed? Whether or not you can use your... Okay. Wait. Look at this problem. Hold on. What are you doing? Matching. And what do each of the matching answers have? Oh. So you wouldn't solve that thing by hand. What would you do? Throw it in your calculator. You could have the pi inside, you could have the pi outside, but you need to make sure you have this whole thing. Well, minus 0 doesn't count, but this whole thing squared. Go ahead and make a match for me, cool kids. If you already had that, you already threw it in your calculator. If you didn't already have that, you're throwing it in now. It's which one? E? But Patricia, divide E by pi. I'm just curious, if someone forgot the pi, is that answer up here too? Ooh. You see how nasty they are? This one has the pi, that one doesn't. Could it be easy for some of you guys to forget the pi? Just be careful, and you're going to be like, yay, it matches, and you're wrong because you forgot the pi. Careful. But what does that bring us to? Volumes of solids of revolution. Now, here's a dilemma. If you are a perfectionist when it comes to drawing, you are going to hate the notes today. If you're a perfectionist for drawing, you're going to hate the notes today. I'm going to get you guys started on notes. As I pass out chapter 5 tests, finally yesterday afternoon, the rest of our people that needed to make it up got it taken. So that's good stuff. The rest of you guys, it's been in RenWeb just a little bit. Remember, on Google Classroom, it's not a specific assignment. I mean, it is in that it's worth points, and it is in that it's required, but it's not in that it's not going to email you reminders, et cetera, as far as the due dates. But what do you need to have done by today's Wednesday? I said before homework is due, so tomorrow, Thursday. What do you need to comment on? Good. Do you have to watch all of them? No, you just have to watch enough to pick a favorite. Comment on the online tutors post. I was trying to make it not as complicated by not making it an assignment. I should have just made it an assignment so that way you guys could get email reminders. I apologize for that. We don't do those very often, so I did it the easy way in my head, but it was actually the hard way for you guys. But the reason why I wanted you guys to pick a favorite one is once you pick a favorite one, then you can watch the videos not just on cross sections, but also on discs and washers. And not just discs and washers, the basic idea, but almost all of them in some way, shape, or form have harder examples as well. And Con and Patrick should also have, especially for discs and washers, AP practice as well. Dr. Marchese, or however you say her name. I don't think she is as focused on the AP, but she is very focused on the topic, which is helpful. Oh, that's what I was supposed to do during zero period. Don't worry, it's not you guys. Struggle. Okay. You guys can peek at your test for just a little bit, but then put it away. The multiple choice were worth 8 points each. There were only 4 of them. At least the first page, I should say. Everything else was kind of worth different things here and there. The slope field matching was worth 3 points each. The long answers were worth like 4 points each part. The FRQ was worth 9 points, and each of the 9 points were worth 2 points. Sorry. I should say names, that way you guys don't. Rebecca, here you go. Ruth, here you go. But we are going to definitely need to work on these corrections, right? Yours, there you go. Allie, there you go. Janelle, there you go. David, there you go. Christina, here you go. Thomas, here you go. Okay, you go. Is Joyce on the journalism trip? Okay. We're not going to take it today, but we will maybe at the very beginning of tomorrow, maybe a few days next week. You guys will have a little bit of group time to collaborate. But remember, we do have a test coming Tuesday, so that's kind of our first priority as far as class time. But I will try to get you guys at least a few next Wednesday for sure. Maybe we'll have it due Thursday, so you guys have a couple days after the test to kind of be able to ask questions and get things answered. But I think we'll have a group time tomorrow also. So if you want to peek at it a little bit tonight or even just right now, I am going to have you guys put them away in just a second. But if you can have like a question or two ready for your group that you know that you got stuck on, need some help on, etc., that would be a good thing. But also for those of you that haven't started homework yet, as soon as you see today's, like as soon as we finish today's, I should say, notes, you're ready to tackle it. You are ready to tackle that homework. All right, speaking of homework, we're coming back to notes in just 1 second. But first, oh, that's not what I wanted. I'm sorry. Here we go. I hadn't opened it yet. Okay, I want us to peek really quickly at homework because I just brought up a really important question that I've heard from a few people this morning, and it had to do with how do we solve once we figure it out. Because just a moment ago in our notes, it was really obvious you're allowed to use your calculator. It's a calculator permitted question. It has decimals. Just throw it in and make it match. But in homework, it's a little bit harder sometimes, right? So let's go ahead and look at homework really quickly. That's just getting ready for an illustration. And let's see what homework or how homework is giving directions so we kind of know what to do, all right? So the beginning of homework, set up and evaluate the integral that gives the volume of the solid. Doesn't say anything about using a calculator, so that would be by hand. Does it mention a calculator at all? Ooh. Down here in number 39 to 40. Use the integration capabilities of a graphing utility. Okay, I'll make you a deal. Where possible. Wait, this one also says use the capabilities of a graphing utility. Now this says to verify, but it still seems to indicate that it's a little bit tricky. That one doesn't, that one doesn't, that one doesn't. Okay, we'll say starting in on number 35, the pink one and beyond. If there's any place where you can use your calculator, go ahead and do so. So 35 and beyond, any place that there is. Now, some of these it would be good to do by hand. I'm a little worried if you guys just start thinking that your unit circle isn't necessary. Unit circle is very necessary, but that's okay. We'll say starting on 35 and beyond, when they start talking about a graphing calculator, you can, after setting up the integral expression, you can use your calculator to solve. That's a little bit discouraging because back here that means 1 through 34-ish, not that you're doing them all, but I'm saying to do them by hand. However, let's say, just because I know it's going to take time, and my main concern is that you guys know how to set up the integrals, not necessarily that you kill yourselves in the sense of having to work so hard at solving every single one by hand. Let's say every other one. Every other one you guys can use a calculator on. Do you guys know what I mean? So like the first two, let's just assume you guys have 1, 2, and 3. 1 and 2 you would solve by hand. 3 you'd be like, whew, all right, let's just plug it in the calculator. 4 and 5 solve by hand. 6, whew, we can use a calculator. Now, those aren't necessarily the ones I assigned, so be careful. Only of the ones I have assigned, but every other one, like every other odd, but every other problem, you guys can go ahead and use your calculator on. Or we'll say every third. That sounds a little better. Every other is like every other odd, and that gets a little confusing. So every third. Because I don't want half of it to be calculator. I need you guys to practice by hand some, but you will be allowed to use your calculator every now and then up until the 35, and then at 35 and beyond, you can just use your calculator to solve. But be careful. If the back of the book gives you some sort of, like, I don't know, with pies or e's or some sort of answer, you're going to have to compare the decimals, right? Does that make sense? Okay. All right. Section 6.2b, volumes of solids of revolution. Put those tests away if you have not yet done so. Let's get them out. Our book actually, I think the pages are a little bit different. I think this was from a previous book. So ours is pages 418 to 424. Let's change that real quick. 418 to 424. That was an older version. But the long story short is somehow we are bringing in the word revolving, or did they use revolving in that AP question, or was it rotating? Okay, but you guys get that they're the same idea, right? Whether you're rotating or whether you're revolving, either way, they can use either word. And we're always going about some sort of line. Now the struggle is that could be the y-axis, that could be the x-axis, or that could be a special y equals line, horizontal line, or x equals line, vertical line. They're not going to give you a diagonal just because that's a little bit too extensive for our purposes. But you're going to be revolving about some line. And then you have to be thinking about what's going to occur. Now there are two different things that can occur. I'm going to actually not do many examples until I've shown you both discs and washers. If anybody looked at online tutors, these two topics are usually put together. And if you notice, I didn't specifically put it in the title because the title is just dealing with solids of revolutions. But there are two different ways of dealing with these. So I'm going to go ahead and really quickly move this guy up above the examples so that we're ready to talk about both methods first, and then we'll start on examples. This is like what we just did. So let's go ahead and see if this work down here makes sense. If you have a region, like a section 6.1 region, an area between a top minus a bottom, or I guess if it's oriented differently, maybe a right minus a left. If we have a region that's being spun such that the region is flush against the axis, which is different than having some space between it and the axis. You guys see the difference? It is possible that we have some hollow And we're going to use that word in just a bit with washers. But discs say, no, 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 there's no hollow space. It's a completely solid figure because when you spin it, there is absolutely no space. Now the space could be here or here or here. If it deviated at all from the axis about which it's spinning, it would be a washer, not a disc. But this disc, if you guys notice, now hold on, wait a minute. Oh, what am I showing you, a three-dimensional slice or a two-dimensional slice? Yeah, a two-dimensional slice. How would I make it a three-dimensional? Okay, and so number one, it would kind of be a little bit jagged, right? Because it would be like what we saw yesterday. There would be a little bit of, it wouldn't be as smooth and rounded and curved. But why am I showing you not just the circular cross-section, but also the depth? What do I want you guys to realize for this one? It's dx, good. Which is why I have dx down here. I am going to do top minus bottom, just like I've always done with dx, except instead of making or having this volume just come and grow out of the area being spun is actually forming that third dimension. So this region to begin with is my R. Top minus bottom is my R. And pi r squared, well, you guys know, pi r squared is my area formula. So I'm really just doing volume is equal to the integral of area, but my area is pi r squared. And because this is spinning, well, then top minus bottom is my r. It's not a diameter like that semicircle that grew straight up out of this. It's being generated a different way. And so, since we're going to have circular cross sections, then we can go ahead and say anytime we have any solid where a region is what I'm going to call flush against the axis, meeting it at every point, the axis of revolution, whatever it is that you're rotating about, as long as that region is flush against when it's spun, I can just say, cool. Who's my x-bound to x-bound? Pi times r squared will be pi times top minus bottom squared, all in terms of dx. But just like the other card with cross sections, that yellow is not going to work well, sorry. Let's try black. I use, instead of having to draw the picture, because the pictures get a bit more complicated, I use the rotation arrow that we used last year when we were rotating things, right? I use the rotation arrow to see whether it's going to be a dx or a dy. And that's the visual way of doing it. Like with cross sections, you could just memorize. You could just memorize anytime there's a horizontal axis of revolution, always dx. Anytime there's a vertical, always dy. You could memorize just like we did with perpendicular to the x, perpendicular to the y. But if you guys saw what I just did, I basically am using, not even having to get the whole pretty shape. I'm just saying from the rotation arrow, like, okay, if this was to spin, then I'm looking here and say, if I give this circle depth, oh, hey, that's horizontal depth. And if I give this circle depth, oh, hey, that's vertical depth. Do you guys see what I mean? You could memorize it according to the forever card. We're on forever card number 45. Because cross sections was 44. But you can give that rotation arrow and it'll lead you to the dx, it'll lead you to the dy. And guys, it's as simple as that as far as if the region, once again, is flush against, because you will have a solid with absolutely no hollow anywhere. Using circular cross sections, because as soon as we rotate, as soon as we revolve, it's going to be circular. Anyone who's taken woodshop, I kind of like the idea of a lathe. Not that a lathe is taking something two-dimensional and rotating it to make the third dimension, but that idea of rotating and what shapes look like when they are rotated. These solids of revolution could be made by hand with a lathe. But if you were to slice it and look at it, the slices would be circular. Which is why we're doing pi r squared. Remember, technically, for one of these discs that is a little bit off, that would make it a little bit jagged, like our example. Wherever he is, here he is. He keeps on getting lost. Like this guy. Remember what the integral does. The integral says, no big deal, pi r squared h, or pi r squared depth, But make the depth dx, I'll make them infinitesimally thin, I'll figure out what it converges to and get you the perfect, smooth, solid volume. So what's different with this guy? Well, let me give you guys a second, because some of you are going to love drawing this and some of you are going to hate it. Long story short, though, you're not going to have to draw these perfectly. And I'm not going to try to draw them perfectly. The ones that you see up here I did on my iPad when I had much cooler like tools and shading and stuff to work with. I didn't do it on a smartboard. If you're just drawing it with a pencil, most of us, we're not artistically talented enough. Some of us we are. What a day for Joyce Kim to miss. Anyway. Washers in general will always be formed when something is rotated and there's some sort of hole. Some sort of hole. It doesn't have to be the whole time. Maybe part of it's solid and part of it's hollow. Maybe the hollow part didn't start until up here, and maybe it was just like hollowed out up here, just at the very, very top. But why is it called a washer? I didn't realize until a couple of years ago that literally, at least in these days, most kids don't know what a washer is. It's kind of sad, actually. They're like, no, it's where you do laundry. What I'm talking about. Now, this is not specifically a washer, but it does go around this little and it keeps this little thing held in. But this is the idea of a washer, right? A washer, oh, I lost it. There's a little metal, there he is. A little metal disc with a little hole punched in that usually goes around screws, not nails, around screws, so that when it is screwed into whatever hard surface you're trying to screw it into, a little extra, I shouldn't say barrier, a little extra, what would you guys call it? It makes it, right? Like it makes it tighter, it makes the fit stronger. I should probably ask someone like Home Depot as to what a washer actually does. I think it protects the surface just a little bit. Instead of like the screw going tight into the wood or something, you actually have that little region that it's going tight against and then it's going more smoothly against the wood. Although you can have marks from washers too if you like screw it in too tight. Anyway, yeah, it forms an extra barrier. I guess that's the best way of putting it. But do you guys see that little cross section? It's a washer. Some washers are thick, most washers are thin. But either way, it's a washer. It has a little hollow area. So what do we do with washers? Do you want me to tell you what the AP is going to hope? I shouldn't say that. I shouldn't say that. They don't hope that you make mistakes. The most common wrong way of doing it, I've never done this before. I've never actually showed the most common wrong answer first. The most common wrong answer says, hey, top minus bottom. Look, I see him. Yay. And it says, no big deal. I'm still going to go ahead and do pi times the integral from whatever a to b I have. It's still going to be a dx, because if you guys notice, doesn't that still have a horizontal depth? And then just do top minus bottom. Squared. No big deal. Top minus bottom, look, it's that guy. Here's the struggle. That's not how most three-dimensional objects with hollow parts are made. That's sadly not how most three-dimensional objects with hollow parts are made. Now, if you've ever been to like the Krispy Kreme store in Burbank, you guys know the one I'm talking about with the mirror or the window and you can see in as they're making all their donuts? I would love to use a donut as an example for this, but it doesn't actually work because the donuts, they actually kind of punch out the dough into the little, like with the hollow. But do you guys know why these are called donut holes? Let's go with that. Why are these called donut holes? Because people would think it's a donut, but donuts have the little psh, psh, psh in the middle, so this got punched. Oh, it's a donut hole. It got punched out. How'd the donut get the hole in the middle? They punched it. Now, did they? No. No. But that's why it's called, okay, this is a big donut hole. But you guys have seen like the cute little like circular ones. But that's why they're called donut holes. Why? Because donuts have a hole. Oh, something went there. Oh, there it is. That's not how they're made. That's the hard part. If you would go to the Krispy Kreme store, you'll see they're like punching things out and then throwing the pieces away. They're going to waste product, right? Maybe in the olden days, maybe that's how they actually made the donuts. They actually had like dough and they punched it. Like, okay, here, let's just make something out of you. But anyway, right? You punch out a donut hole. You have to subtract. Now, I don't know exactly how Mr. Horn does woodshop. I knew how Mr. Hogan did, because I would watch kids walking around and they were making, one of their first projects was always the bowl. And so they would have like the sandpaper and they'd just be sanding and sanding and sanding and sanding and sanding, trying to make it smooth. They would use a chisel, but then they would sand and they would sand and they would sand to try to make that bowl perfect as far as what was going on. If you're doing something in woodshop and you're trying to hollow something out, don't you have to actually take a solid and then actually get it out, right? Different than a donut hole, because they don't actually make it like that. We have to take the whole thing, and then we have to subtract the hollow. So I want you guys to look at the formula and see if it makes sense. Unlike donuts and how they're actually made, and donut holes and how they're actually made, I want you to think instead woodshop and think some sort of solid block of wood, and you want to make something out of it. Or if you want to, you could think about the potter. I know you guys were all mocking her, although I thought it was a really cool illustration. She just needed like a camera zooming in on her hands. That would have been cool. Mr. Hogan and Mrs. Reiser, I guess now we're getting to people not knowing people that retired. But they did a chapel once where Mr. Hogan was on his potter's wheel and the camera was zoomed in and he was just making the whole time and Mrs. Reiser was talking through an illustration. It was pretty cool. But you can think the potter too. Didn't she just start with a clump of clay? Or lump of clay? Man, this is horrible, but a clump is a word too, right? A lump of clay. And wouldn't she build it up and it would be solid in between, but then what did she start doing? Wouldn't she punch it in, right? And she would start making that hollow. That's the same idea here. I have to think of a solid. I have to think of a solid that's formed by disks, pi r squared. I have to think of the solid. Then I have to think of the hollow. If the hollow was a solid, think of its volume. Think of the volume of the hole. Think of the volume of the hollow. And then I have to take it out. I have to subtract. It's a very natural process, but our brains are going to be like, top minus bottom, no big deal, throw in the R. And it's incorrect. It's going to give you a very wrong value. Because it's going to be taking that top minus bottom and it's going to be spinning that around. So it'd be like this being spun around this axis. If you did that top minus bottom, it would be like a teardrop. This is not a teardrop. It's going to have a very different volume than a teardrop. So I can't just do top minus bottom because that would be working off of this axis and spinning him. I have to think, no. Ignore the hollow. Just look at the outer edge. Look at the outer edge. And what volume would that give me? Then look at just the hollow. Ignore the solid and pretend what was taken away, what was subtracted, and find that volume. And then subtract the two. So it's the whole minus the hollow. And that gets us to our forever card, where it's not top minus bottom is the radius squared. No, it's big radius squared, pi, big R squared minus pi, little r squared. Pi whole radius squared minus pi hollow radius squared. And be careful. When I say whole, do I mean like donut hole? No, I mean whole thing, right? So be careful. I used to do whole minus whole, and then it was just super confusing. So it's whole minus hollow. The whole thing minus the hollow part. That's whenever we have space between the region and the axis. Now I have glaze all over my hands. Okay. This is 46 now, right? And the last forever card from new content of the year. Might get some more forever cards in AP review time, but for right now, the last forever card. of new content for the year. Ooh, hey, if the test is Tuesday, when's our forever quiz? Ooh, some of you should put a reminder in your phone because you're not going to remember. Monday, how many cards do we have? Area, volume cross sections, volume discs, ooh, volume washers. Okay, we have 4 cards. But no theorems, no definitions, right? Just formulas. A few illustrations. Guys, do you see why I'm going to come and put little depth on this guy? And just say dx. Is that okay? Put a little depth on this guy. Just say dy. Because in my head, visualizing makes it easier. And I'm not going to force you guys to draw these pictures because as you can see, they get confusing. They can be fun if you're artistic, but they can also be a little bit rough. So here's what's actually going on. I'll come back to this in a second, but what's actually going on, I'm going to label big R and little r in this figure. So big R is going to be from the outermost edge, from the edge of the entire solid, all the way to the axis of revolution. That's going to be my big R. The outermost edge, totally ignoring the hollow, totally ignoring what was taken out. The outermost edge to the axis. Or you could also think, depending on the problem, it's easier sometimes to think the axis to the outermost edge. Whichever way you measure it, outermost edge to the axis, axis to the outermost edge, you will have the distance for big R. However, we don't just have a big R. What else do we have? A little r. So our little r, we might need to get a little bit darker. Our little r is going to be the axis to the edge of the hollow. The axis to the edge of the hollow. Our big R is going to be from the axis to the outermost. Our little r is going to be from the axis to the edge of the hollow. Now, I just showed you 2 representative slices. I could have put them directly on each other. That might make a little bit more sense since they're different colors. Maybe I can. But then it starts to get a little bit confusing for most of you. I could have put them on each other, and at this slice for this disc, I would do the entire disc, and then I would do the part that gets punched out or subtracted out. I put them side by side just because it's a little bit easier for my brain to process if they're not directly on each other as far as big R and little r. But remember, that's a representative. My integral is going to take all the different slices and put them all together the same way, the right way, and it'll be fine. So we're just showing a quick representative for our brains to realize, oh, green minus axis and red minus axis. Now, quick illustration. I have this guy open. I like this one for discs because it kind of shows you what's going on as far as how this rotation works. But if you guys realize the difference between a disc and a washer, then you'll realize. Now they're showing rings, surface area. Don't worry, that's something that BC does. It's called a frustum. Anyway, we don't have to do surface area of these solids, but here's what we're doing. We can't make it nice and smooth. What we can do is we can do the jagged and put the cylindrical into an integral, and the integral will go ahead and make them infinitesimally thin and make them the nice smooth that we need. But that's a solid, that's a disc, right? For washers, I have some illustrations, but let's do a couple examples, at least just setting them up before we leave. We're just going to do 2, okay? Just these 2. Remember, we still have until Friday. We're going to have a whole nother class tomorrow where we're just doing examples, okay? But this is getting you the idea. Let's just look at these 2. Let's just look at these 2. This one's called a disc, and what do you guys think this one's called? A washer. Remember, homework can have cross-sectional areas. That's like the puddle on the ground. Something's growing up out of it. But then it can also have revolution, rotation going on, and that's where you're actually taking a region, revolving it, and getting or making the 3rd dimension. My question for both of these, as you guys are setting them up, dx or dy? Now, you're hoping dx because everything's in terms of x. Oh man, if it's dy, I have to solve for a lot of x's. But also, yes, dx, because how is the revolution going? Around a horizontal axis, which we could memorize, so yes, dx, around a horizontal axis. I don't even need to draw my whole shape. Which formula is less complicated, the disc one or the washer one? Disc one. When I spin, right? Don't I have an area of pi r squared? We can start with the cross-section idea. Area is pi r squared every time you spin. Volume is equal to the integral. Is it okay if I just pull pi out? Danger, danger, danger. It's okay to pull a constant out, but what could be easy for you guys to forget when answering with an integral expression or plugging into a calculator? Don't forget him. Why am I just going to do 1 squared there? Versus, same thing here. Same thing here. But why am I doing this down here? Do you guys see the hollow? It's a washer. I have to punch out the donut hole. Oh, that's a horrible explanation. I need to pull out, subtract away the hollow. Okay, so coming back to the disk. What do you guys see for your bounds? I'm going to need a little more space. I'm spreading him out. What do you see for your x bounds? -1 to, got it. You see it? How left, how right? X value to x value? How do I get my radius? It's only 1 radius. Just top minus bottom, no big deal. Nothing got subtracted, no big deal. Top minus bottom, it's solid, no big deal. Cool, so who's on top? Who's on bottom? Got him, coach. Couldn't we go ahead and simplify this then to be pi -1 to 3 minus 0 goes away as square root squared? Isn't it just 3 minus x? Why does it look so weird? Because the square root got squared, but was pi r squared here? Yeah, just got simplified. But what's going on down here? Do you guys see your big R versus your little r? Would it make sense if I show 2 minus x squared minus 0 and then x minus 0? Because it's parabola minus axis, line minus axis. Dun, 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 dun. Could you simplify it, I suppose? Discs, washers. If you haven't yet done it, choose your favorite tutor, watch their cross-sectional video, and then be like, okay, so dishwashers. Maybe I'll watch their dishwashers video too. And then start homework. Bye, guys. See you later, Gators. Today, I will not be here after school. I apologize. Unless something weird happens and I get to stay, I think I'm going to be gone. So catch me during lunch if you need me.
Since I'm going to be on Monday, should I take the Forever Quiz Friday or when I get back?
Whenever you're ready. Whenever you're ready. Because we could do